Cross-link density in polymers refers to the concentration of covalent bonds, cross-links, connecting individual polymer chains, forming a three-dimensional network which dictates material properties like strength, rigidity, and solvent resistance. It's measured indirectly through methods like swelling tests, ASTM-D2765, dynamic mechanical analysis, DMA, or rheology, where higher density leads to increased hardness, better thermal stability, and reduced swelling, while lower density results in more flexibility. The structural complexities of polymer networks, i.e., multiple functional groups, diverse connection sites, and various defects, make it difficult to accurately describe their microstructure using theoretical models and traditional metrics, such as the cross-link density. Macroscopic properties of polymer networks are closely linked to their microstructure, which refers to the detailed arrangement of the constituent elements at a microscale, with the network topology being a crucial parameter. Nevertheless, the insolubility of chemically cross-linked polymers makes experimental characterization challenging, hindering the accurate prediction of polymer network behavior, particularly in systems with multiple connectivity and functional groups. Additionally, several statistical theories have been developed to correlate the network topology and viscoelastic properties. While these models effectively determine average macroscopic properties in many cases, they often assume an ideal network formation and largely overlook the network defects, including various loop orders and free or dangling chains. These defects deteriorate mechanical performance and affect the material's durability by lowering the overall elasticity of the network. Characterizing the microstructure of polymer networks through experimental techniques is challenging, particularly in capturing topological features. Among experimental methods, dynamic mechanical analysis (DMA) is a standard technique for quantitative analysis of cross-linked polymers, e.g., measuring cross-link density. In this method, cross-link density is estimated by applying classical rubber elasticity theory to the elastic modulus measured at the onset of the rubbery plateau. However, this approach can be inaccurate for complex networks, as it relies on the assumption of an ideal defect-free network structure, which becomes unreliable when the network contains many defects. The distribution and presence of defects in the network significantly change the thermomechanical properties, especially in complex systems. The degree of cross-linking in a thermoset is a critical parameter that has a major influence on the mechanical strength and viscoelasticity of the material. For an unfilled thermosetting polymer, the percentage of cross-linking or the cross-linking density can be quantitatively calculated using both rheological and DMA measurements. Dynamic oscillatory testing is a very important method for characterizing thermoplastic and thermoset materials. It is usually the best way to determine a material's viscoelastic properties, which can be related to molecular architecture, processability, curing kinetics for thermosetting materials, and end-use performance. In dynamic testing, one imposes a sinusoidal strain at a particular frequency and measures the resultant stress, or vice versa. Imposing a sinusoidal strain and measuring the resultant stress in a shear deformation mode. Measuring and calculating the cross-linking density of a thermoset. Dynamic temperature ramp of a non-cross-linked adhesive above Tg. The storage modulus of the polymer shows a plateau over a temperature window between 40 degrees Celsius and 70 degrees Celsius. Then, at temperatures greater than 70 degrees Celsius, this polymer becomes molten with the loss modulus being greater than the storage modulus, and the sample flows like a viscous liquid. The value of the rubbery plateau modulus is correlated with the polymer chain entanglement. If the polymer is partially cross-linked, then its molten state will not be observed in a temperature ramp test. After Tg, the rubbery plateau area will extend up to higher temperatures until the polymer starts to decompose. The storage modulus remains greater than the loss modulus at temperatures above the normal molten temperature of the polymer without cross-linking. For a cross-linked polymer, the storage modulus value in the rubbery plateau region is correlated with the number of cross-links in the polymer chain. There are several references in the literature reporting the use of the modulus measured within the rubbery plateau region to quantitatively calculate the polymer cross-linking density. Equilibrium swelling, ASTM D2765, is a standard test method for determining the gel content and swell ratio, a measure of cross-linking, in cross-linked ethylene plastics, by immersing samples in a solvent, like xylene, at a constant temperature, e.g. 70 degrees Celsius, 110 degrees Celsius, until they reach a stable, swollen state, then measuring the weight or volume change. This test assesses the quality and uniformity of cross-linking, indicating network density. Tightly cross-linked materials swell less, while loosely cross-linked ones absorb more solvent. In a typical experiment, the sample is submerged in a specific solvent, e.g. xylene, at a controlled, elevated temperature, like 110 degrees Celsius. The sample swells as the solvent penetrates the network, eventually reaching equilibrium, where swelling stops. Finally, the swollen sample is removed. The solvent is carefully removed, e.g. by drying, and the final weight, wet weight, WW, is recorded. Swell ratio, wet weight minus dry weight, divided by dry weight. A higher swell ratio means lower cross-link density, looser network. Molecular dynamics simulation is among the most successful methods for modeling polymer networks through a reactive scheme. It accounts for the stiffness of prepolymer chains through explicit force field parameters such as angular and torsional potentials, steric hindrance of surrounding chains, which affect reactive groups' accessibility, and the evolution of the spatial arrangement of chains and crosslinkers during the reaction. Therefore, various researchers employed molecular dynamics-based reactive schemes to construct a reliable network structure, able to predict many properties that were in good agreement with the experimental results.